Hello friends, so today we are going to solve 3 questions, and these 3 questions are from your collision, conservation of energy as well as momentum. Okay. So the first question, and 1 second. So in the first question, it states that a force-free rocket ejects gases at constant speed u. At what remaining mass is the rocket's momentum maximum, and what mass is its kinetic energy maximum? So we have to find out the respective kinetic energy as well as the momentum. That will be the maximum part. Okay. So in this case, we can assume certain things which are not given in the question. We can say that the initial mass is suppose m0, is our m0, and the remaining mass after some time is suppose m. Remaining mass after some time is suppose our capital M, and it is the speed of the exhaust gases is given to us. Okay. So we can rewrite this, that exhaust speed relative to rocket is u. Okay. And it is given in the question there is no external force, that is a force free. So obviously we can use the conservation of momentum. So first of all, let's find out what will be the velocity of the rocket. And if you know the this is standard formula also, so if you know the formula you can directly solve it, or if we want to drive it, it's quite simple to drive also. Okay, so let's find out the rocket velocity when the mass is m. Rocket velocity, let us call this as our v of m. Okay. And so at any instant, let us consider that the mass in the rocket mass is our m, that is given in the question. So we start from there only. So we say at any instance rocket mass is our capital M, and rocket velocity is suppose v. And for the sake of convenience, let us assume that it ejects a small mass, that is our dm. It ejects a small mass, and let us suppose that mass is our dm. And let's find out our momentum before the ejection of this small mass. Okay. So we can say that our before ejection momentum and let us call this as our pi, that will have initial will be equal to mass into velocity, and after ejection we can write rocket mass will be equal to m plus dm, and rocket velocity will be our v plus dv, and the ejected gas mass will be our dm, and that will be of the negative sign. Now we can find out the gas velocity in the lab frame. Okay, that is basically our relative velocity. So we can say our gas velocity in our lab frame, that will be equal to our v minus u, and we can write down our final momentum. So you can say our after momentum, let us call this as P final, will be equal to mass and velocity, and because of the gases also, so this will be over plus minus of dm, and this comes as v minus u. A simple conservation of momentum. Momentum conservation. So we can say our initial is equal to final. So we substitute them, we get our mass into velocity will be mass plus dm v plus dv minus dm v minus u. And this is now simple calculation. We are interested in finding out the velocity v. So let us open our right side. So that will be giving us m times v plus m times dv plus v times dm, and then it will be plus dm and dv minus v into dm plus, and that will be u times dm, and these two terms we can easily cancel out. Okay, and we can just ignore this part because this will be a product of very two small things. And so, and on the right side we are left with our mv, and this mv and mv are also going to cancel out, so we will be left with only our two terms, that is our m times dv plus u times dm is equal to 0. Now we can easily form this as a differential equation, and we can say that our dv is equal to minus of u, and this comes as dm upon m. And now we can just integrate it, and for the limit of integration, when velocity was 0 and final velocity is over v, so when the velocity was 0, the mass was m naught, and when velocity is v, the mass is over m. So this we can easily calculate, right, with the help of our initial condition. And so this derivative of rather 1 upon m will be natural log of m. Therefore from here we can write that v is equal to u natural log of our m naught upon m. So this formula, if you know, you can just directly use it. And sometimes it is also called as a rocket velocity derived from first principles. So these things is also. And now we come to our main question. That is our momentum of the rocket, because we found out the velocity. So we have momentum of rocket, and the momentum of rocket, that is our p of m, will be equal to, or our mass into velocity, and velocity we just calculated. So we can write this as our p of m is equal to mu natural log of m naught upon m, and we have to maximize it. Okay, so we need to differentiate. Before that, let us expand this logarithmic part. So we can write this as mu, and we get this as natural log of our m naught minus natural log of our m. Now we can easily differentiate it. So we get dp upon dm, and that will be equal to u, and we get this as natural log of m naught minus natural log of m minus 1, and we are going to put equal to 0. And so we can, because this velocity cannot be equal to 0, so we can write this as our natural log of m naught upon m is equal to 1. So therefore from here we get that our m is equal to m naught upon e. So this is our value of mass for which the momentum is maximum. Now same way we are going to calculate for our kinetic energy. So we can say that kinetic energy is, let us suppose, our k of m, and that is equal to half m v square. V already we know, so this comes as half, and we have this as m u square, and natural log of our m naught upon m whole square. Once again we are going to maximize it. And for the sake of convenience, let us assume that this term is equal to over x. That is helpful in solving the differentiation part. So we say that our x is equal to natural log of m naught upon m. Therefore we can say that our kinetic energy is equal to over half u square m x square. Now we derivate it, and we have to remember that we are going to derivate it with respect to our mass m, and our x is also dependent upon our m. Okay, so that's not independent. So this comes as our u square upon 2, we can take as common. So this will be coming as our x square plus m times 2x, and this comes as a dx upon dm. But we know that our dx upon dm is equal to minus 1 upon m. So we can just substitute it, and from there we get this is equal to u square upon 2, and we have our, this is x square plus 2 max and minus of, this will be coming as 1 upon m. Okay. And so one second, something is missing. Two x square, 2 max. Oh, sorry, it's a multiple. My mistake. It's a multiple. And this m and m cancels out, and this is minus. And so from here we get u square upon 2, and we have our x square minus 2x, and derivative for maximization equal to 0. So from we get x minus 2 is equal to 0, and so obviously the solution will be our x minus 2 is equal to 0, giving us x is equal to 2. And we know that our x is our natural log of our m naught upon m is equal to 2. So from here we get that the value of m is equal to m naught upon e square. So this is the value of the mass for our kinetic energy to be maximum. We can do the second question. So in this second question, it states that a tennis ball of mass m2 is placed directly above a basketball of mass m1 with m1 is much larger than m2, as in figure. Okay, so figure is given to us. The bottom of the basketball is initially at a height h above the ground, while the bottom of the tennis ball is a height of h plus d. Two balls are released simultaneously and fall vertically under gravity. The basketball strikes the ground first and rebounds elastically. Immediately afterwards, the basketball collides elastically with the tennis ball. Assuming all collisions are perfectly elastic, the balls are initially separated by a very small distance. Each collision occurs instantaneously. Determine the maximum height reached by the tennis ball after the collisions. So basic figure is given to us. Okay, so we have this B1 ball, which is our like a basketball, and its mass is given as our m1, and B2 is a tennis ball whose mass is given as our m2. And in this picture these are very closely, but in the question it is mentioned that one second. Yeah, they are initially separated by a small distance. Okay, that is mentioned in the question. So actually we can say that suppose this is our B2, then this is our B1. Okay, there is a small distance between the two. That's the basic question, because this approximation is going to help us to solve this our h plus d. Okay. And everything is elastic, okay, and m1 is much larger than m2. So we have to remember this thing. So let us find out that when both are being released, it is given that the basketball hits the surface first. So let's find out what will be the, you can say, speed just before the basketball hits the ground. So that will be the first part. So you can say that our speeds just before basketball, let us call this as a B1, hits the ground. And the mass of this basketball is given to us as our m1, okay, and it falls from the height h. Okay, so we can simply use energy conservation. So you can see our energy conservation. And let us assume that just before it hits the ground, its speed is given as our v1. Therefore, we can write that kinetic energy half m v1 square is equal to its potential energy, that is m1 h gh. Okay, and this is our m1. So these two terms cancel out. Therefore, we get that just before it hits the ground, its velocity is our v1, which comes as our 2gh and its square root. Okay. And now we come to our tennis ball. Tennis ball, that is our B2, and its mass is given to us as m2, and the height from which it falls is our h plus d. Okay. So once again, let's assume that its velocity just before hitting the ground is our v2. So let me put it here, so you can see its velocity is our v2. So therefore, once again, our energy conservation, and we can write this as our half m2 v2 square is equal to m2, and this comes as h plus d. And we can write that our v2 is equal to 2g h plus d and its square root. So this is our velocity of the tennis ball, and when just before hitting the ground. But like I said, that there is a small gap between the two. So from this we can say that the height h is much larger than the distance d. And so this is going to help us to resolve this particular equation. So for that, we can say that our d is very much less than our h. Therefore, we can say that our 2g h plus d and square root, and we can write this as our 2gh and square root, and this comes as 1 plus d upon h and its square root. Okay. So obviously this ratio will be very small. Ratio means this d upon h. Therefore, we can say this is approximately equal to square root of 2gh. Okay. And the square root of 2gh we know is our v1. Therefore, we can say that our v2 is approximately equal to v1, and let us say that is equal to our v. So based on this, so it means that the approximate velocity of both our basketball as well as tennis ball speed is same just before hitting the ground. Okay. And it is also given a question that basketball hits the ground first. So let us discuss that situation now. So we can say that basketball is our B1. So we can say B1 ground collision. And collision is elastic. So we can say obviously the velocity of the basketball after the collision is going to remain v, but the direction is going to reverse. Okay. So we can say that our collision is elastic, therefore we can say that B1 speed, B1 is a basketball, B1 speed is going to remain as V, but direction reversed. Direction will be reversed. So it means before impact, or we can say that, after impact rather, before impact we already know, therefore we can say that our immediately after, we can write that immediately after collision, our basketball, that is our B1, is going to have our speed, let us suppose that is our plus V, and that is upward. But our tennis ball is still traveling in the downward direction, so that is our B2, whose speed is also V, but that will be negative, and that is our still downward, because collision is not taken place between the basketball and the tennis ball, so it is still downward. Now we are going to find out the relative speed before the collision between the basketball and the tennis ball, or we can say before ball collision, B1 B2 collision. You can say that our relative speed before B1 B2 collision, and let us denote this as a V relative, which will be equal to plus V minus of minus V, which gives us twice V. Now we come to our collision between B1 and B2. Okay, so that was before. Now we come to our B1 B2 collision. And collision is entirely elastic, and we have to remember that the mass of the basketball is much larger than the mass of our tennis ball. So let us assume that the frame of reference is our basketball, and for the fraction of second that basketball is at rest, or in simpler term we can say that the basketball's instantaneous rest frame. And basketball is our, so B1 instantaneous rest frame, and under this condition we can easily make a conclusion that the tennis ball will be approaching with a speed of 2v, because their relative speed is our, between the two is Vr, and if our basketball is our rest frame, then the velocity of approach for our B2 tennis ball is equal to our 2v. Therefore we can say that our B2 approach velocity will be equal to 2 times v. Okay. And the collision is purely elastic, so it means the tennis ball is going to rebound with the same speed, that is our 2v. You can say we are having the elastic collision, therefore we can say that our B2 rebounds with speed, and that speed will be also our 2 times v. Now we come to our lab frame. Okay. Therefore we can say that in lab frame we can write that velocity of our tennis ball, that is our B2 after the collision, will be equal to our velocity of the basketball, that is a B1, and then we come to the velocity there. So this comes as our 3 times v. And now we come to our final part, that is height reached, because now we know the velocity of the ball after the collision. Then we simply use the conservation once again. Therefore we can say that immediately after collision, we can say that our tennis ball is our B2. So B2 is height of our D, and its speed is upward. So we have upward speed, and that is our 3v. Therefore our energy conservation and this gives us half m2 3v square is equal to our m2g and h minus d. Okay. And this is quite simple to solve now. This m2 and m2 goes away, and we are supposed to find out h. Therefore we can say that our h will be equal to d plus 9v square upon 2g, and we already know, so we substitute it. So this comes as 9 upon 2g, and this comes as about 2gh, and here this 2g and 2g cancels out. Therefore we get that height h is equal to d plus 9h. So this was a second question. We come to a third question. Third question is the extension of this second question. In this particular question, we were only having 2 balls, okay, basketball and other one is tennis ball. It means with respect to the mass, they are on the decreasing side. M2 was on the higher side, and sorry, not M2, but basketball, that is M1, was on the higher side having the mass, and M2 was on the top of it. Now in this third question, this is a continuous chain. Okay, same question, and a little bit different things are being asked in this question, and for that, sorry, got lost. One second. Yeah. So we can just, yeah. So let me read the question. It's almost same, but with a minor difference, and it states that now consider a vertical stack of n balls labeled B1, B2, Bn with the corresponding masses satisfying m1 greater than m2 greater than m1. The balls are aligned vertically with B1 at the bottom and Bn at the top, as in figure. The B1 is initially at a height h of the ground, while the bottom of the ball Bn is a height h plus L, where L is very small compared to h. The entire stack is released from rest, falls vertically under gravity. Each collision, both with the ground and between the balls, is assumed to be perfectly elastic and instantaneous. in terms of n, determine the maximum height reached by the top ball after the sequence of collision. If h is equal to 1 meter, estimate the minimum number of balls required for the top ball to reach a height of at least 1 kilometer, and part B, reach escape velocity from the earth. Assume air resistance and other dissipate effects are negligible. Continue B as all collision to be elastic. So this figure is only drawn for number of balls, that is over 4. So this B1 is having a mass of over M1, B2 over M2, B3 as M3, B4 as M4, and it goes on up till our Mn. Same, but now we have a n number of elastic collisions, n number of balls rather, okay, collision. And same approach we are going to use, okay, initially, and then we are going to you can say elaborate for it to n number of balls. Basically, once again we are going to discuss 2 balls, and then we come to convert into n number of balls. Okay. And we already know that the velocity of B1, whose mass is m1, just before collision, we can say that our v1 is suppose is equal to v, and that is equal to over 2gh and its square root. Okay. And our top ball, that is our bn, and its mass is our mn. Let us suppose its velocity is given as our vn, and vn, same principle, will be giving us 2h plus l. And in the question it is mentioned that this h is very much larger than l. So this can be approximately equal to square root of 2gh. So therefore we can say that our v1 is approximately equal to vn, and that is, we have said, is equal to v. Okay, the same conclusion as the second question. Okay, there is no doubt about up till here. Now, one thing very sure, we know that because the collision is our elastic, so just before collision the velocity of the ball is, that is b1 is v. So after collision the velocity will be upward for b1, but all these balls b2, b3, b4 will be still traveling in the downward direction with the speed v, when this b1 after collision will be moving upward with the velocity v. Okay. So same process, but now we can just discuss it with respect to n number of balls. Therefore we can say that our immediately after b1 hits the ground, and because collision is of elastic, so only the velocity is magnitude will be same, direction will be changed. Therefore after collision we can say that our b1 is having a velocity in upward direction. So we have upward speed, and that upward speed we know is our v, and rest of the balls, that is our b2, b3 and bn, they are still moving downward, but their speed is equal to our v. Okay. So it means it will be now something like a chain reaction. Okay. And for the sake of convenience, let us generalize this balls. Okay. So lowest one we are going to call this as b of I, and in the top of it we are going to call this as bi plus 1. Okay. So we are going to generalize it with respect to bi and bi plus 1, so we can apply it to any of the ball. So let us write it as relative speed relative speed before BI and BI plus 1 collision. And we know that our BI is moving upward with the velocity v, and BI plus 1 is moving downward with the velocity v. Okay, so there is no doubt about it. Okay, so we can say that we are having BI, the velocity is over v but moving in upward, and we are having BI plus 1, the velocity is over v but it is moving in downward direction. So once again we find out their relative velocity. So you can say relative speed of approach and we can call this as VR. So that will be equal to our VI and minus of minus V. Okay, let us call this as VI. We need to differentiate, later on we can just modify it. So we get our relative will be equal to our VI plus V. And now we come to our relative speed. What happens when the collision is going to take place? And we know that our m of I is much larger than our mi plus 1. Therefore, we can write that our after collision they will be leaving with the same speed. Okay, so we can say relative speed after collision will be our v of I plus v. Okay. And now let us find out what will be the actual speed of our BI, BI plus 1. Same method, so we can say that we know that our BI is moving upward with the velocity of our VI, and relative speed we just calculated is our VI plus V. Therefore we can write that upward speed of BI plus 1, let's suppose that is a VI plus 1 will be equal to VI plus V, and this gives us that the VI plus 1 will be equal to twice of VI plus V. And this will be a, you can say, recursive process. Okay, so we can expand it for n number of times, and this is VI plus 1 twice VI plus V, and we also know that our V1 is equal to V in the first instant. Therefore, let us suppose we can find out our V2. So V2 will be equal to our twice of V plus V, this gives us thrice of V. V3 will be giving us twice thrice of V plus V is equal to 7 of V. And similarly, V4 will be giving us twice 7 of V plus V, and that will be 15 of V. Okay, so this process will be recursive process. And in general, we can write the equation will be equal to over V of n is equal to 2 raised to power n minus 1 times V. Okay. And we come to our final part, that is we are interested in finding the height. And therefore we can say the height reached by the top ball. Height reached by top ball. Okay. And we can use our energy conservation. And this energy conservation gives us our half mn vn square is equal to mn g h minus L. And here this mn and mn cancels out, therefore we get our height h will be equal to L plus Vn, we already know, and this is the square, so this comes as our 2n minus 1 whole square v square upon 2g, and v square we know is our 2gh, so this comes as L plus 2 raised to power n minus 1 whole square, and this comes as 2gh, and this is our 2g, and here 2g and 2g cancels out, so we get that our h is equal to L plus 2n minus 1 whole square times h. So this is the height reached by the topmost ball. So we are left with two parts. So part A in states ask that the height it reaches at least 1 kilometer. 1 kilometer means our 1000 meters. Okay, so we can easily substitute it. So we can say that our part A and part A, it says that it should reach our 1000 meters with h as 1 meters. Okay. So same equation we can put that our reach, that is our 2n minus 1 whole square times 1 should be greater than or equal to our 1000, and from here we can easily find out value of our n, and this n will be our, one second, yeah, so we can write this as our 2n minus 1 should be greater than or equal to approximately, that is equal to 32. So it means if you put value of n, we can write this as our 5 2 raised to power 5 minus 1, which comes as our 31, and when we put n is equal to 6 2 raised to power 6 minus 1, this comes as a 63. Okay, so we can say that the number of balls is close to 6. Okay. And part B, it was here it was asked about the escape velocity, so they included the part of the gravitation here, and that is quite simple. We know that our escape velocity, the formula escape velocity, that is our v escape, that is equal to our 2g and square root r, and for this escape velocity, obviously the velocity or height, that is our, the velocity part should be greater than the escape velocity. So we can say about 2n minus 1 and 2gh square root should be greater than or equal to 2gr and its square root. And 2g and 2g we can cancel out from here. Therefore, we can write this as our 2n minus 1 is greater than our r upon h and its square root. And so we can approximate it for n also, and we can write that there will be a natural log of 2 and 1 goes on the other side, so we can say that value of n approximately, okay, but it will be hold the greater than relationship will be equal to our log to the base 2 and square root of r upon h plus 1. And we know that our radius, that is our capital R, is approximately equal to 6.4 into 10 to the power 6 meters, and h is said to be, given in question, is our 1 meter. And from here we can say that our value of n will be approximately equal to 12. Okay, so these were today's 3 questions, and of these 3 questions, the first one was of our based on the rocket, and second and third question was based on the multiple collisions, and for that the second question specifically was only for 2 objects, 2 balls, one a basketball and the other one was the tennis ball, and the third question was only the extension of the second question, okay, with respect to the number of balls as well as our number of collisions. Okay. And the third question was a little bit extended in terms of our escape velocity, that the gravitation part was also asked in the question. So this completes all the 3 questions for today. Thank you.